relations, they're not the same. When we talk about a function has an input and an output. In addition to that, which is not characteristic to relations, the difference now between functions and relations. So a function has an input and an output. To each input, it corresponds a unique, only one, a unique output. So let's illustrate, and then we're going to see the difference between these two. Two bubbles, two more bubbles, and two more bubbles. Situation number one. The input is called x. Input. Can it be p and t? Yeah, of course. In general is x. The output is y. So what happens is, to this x value, let's say 2, it corresponds 3. It's an example. Let's say to 0, it corresponds 11. Let's say to 5, it also corresponds 3. To each x value, it corresponds a unique y value. So 2 corresponds to 3, and I found an ordered pair, 2, 3. 0 corresponds to 11, 0, 11. 5 corresponds to 3, I have another ordered pair, 5, 3. This is a function. Number 2 is also a function, something like this. To each and every x value, it corresponds to a different y value. This is also a function. But number 3 is a relation. Here's why. Five, 10, 11. And this is a relation. A function makes input correspond to only one output. Even if it's the same for two x values, it's fine. 2 corresponds only to 3. 0 corresponds only to 11. 5 corresponds only to 3. Function, function. This is not a function. It's sufficient to show that any value of x corresponds to two values of y. That contradicts the definition of a function. So this is a relation. Both exist in real life situations. But this is a function and this one is not. Also, I'm just going to show you a few graphs. So this is graph number 1, this will be graph number 2, and this will be graph number 3. So the first graph is this. The second graph is this. And the third graph is this. How will I identify which graph corresponds to a function and which one corresponds to a relation? And there is a very easy situation here, a very easy response. By the vertical line test. So remember what we just said. To 2, it corresponds only 3. to 0, only 11, to 5, only 3. Meaning, by the vertical line test, and this is very important to understand it because this is how we are going to read from a graph. For x equals 4, this is my x equals 4. It meets the graph in one point, and I will be reading the corresponding y value. I'm going to put some values so we can understand the points. 4, -1. For this vertical line, let's say x equals 6, it crosses the graph only in one point, and I will be able to read the corresponding y value. For this one, I'm going to say x equals -2. It meets the graph or crosses the graph in one point, and I will be reading the corresponding y value. So for -2, only one corresponding y value. For 4, only one corresponding y value. For 6, only one corresponding y value. So therefore, this is a function. And we say by the vertical line test, this graph corresponds to a function. In graph number 2, can anyone let us know whether that, by the vertical line test, whether it corresponds to a function or not? Graph number 2, by the vertical line test, does it correspond to a function or not?
Yes.
Yes. For this x value, I read only one y value. For this x value, I read only one y value, and so on and so forth. Function. Can anyone tell us whether graph number 1, by the vertical line test, if this is a function?
No, it's a relation.
Because I found that for x equals 1, I can read two values of y. One that is 1 and one that is 7. So like in example number 3 with the bubbles, I call them bubbles, but actually they have names. This one is called the domain, where x takes values is called domain. Where y takes its values is called range. Initially, I'll call them bubbles because we haven't discussed domain and range yet. So this is a set of numbers where x takes its values. It's called domain. This is another set of numbers where y takes its value. So this is the input, this is the output. Domain, this set is called domain, this set is called range. The same thing for relation as well. This is the domain of the relation, this is the range of the relation. Good. So now about the notation. We discussed the notation when we talked about polynomials. If you remember, I said p of x. That's a function. What we like is f of x, g of x, but it doesn't matter. But remember, we do not read this f quantity x, or f times x, or f of whatever. No, f of x, g of x, which means f is the name given to the expression that follows, and x is the independent variable. So coming back to our first example here, we are given y, but y is the same with f of x. is 2x squared plus 3x and minus 2. Determine whether the given points are on the graph of the equation. So let's choose one ordered pair. It's the same as we did with the other equations that were quadratic or something else. Let's choose the first one. So 2, 12. If 2, 12 is a point on this function, then the point has to verify its equation. If it doesn't verify its equation, it's not on the graph. Meaning, this means x, this means f of x. This is super important. If I have this function, this point here is x, comma, the function value at that point. So if I'm given 2, the y-coordinate has to be f of 2. If it isn't, then this point is not on the graph of the function. So I will replace the left-hand side, or y or f of x, it doesn't matter, by 12. And I'll say, does this equal 2 times 2 squared, which is 4, plus 3 times 2 minus 2? If I say yes, then the point is on the graph because it verifies the equation. If I say no, then the point is not on the graph because it does not verify the equation. So 2 times 4 is 8. 8 plus 6 is 14. 14 minus 2 is 12. Therefore, I will say yes. This point verifies the equation given in the problem. Therefore, this point is somewhere on its graph. Any questions? And the same thing, the same procedure for the other points. This is how we determine whether a point is on the graph or not. So here's a totally different function. This is called an absolute value function. Absolute value. So this is y or f of x, the absolute value of x minus 2. So let's check with -4, -6. Is this point on the graph? I don't know. So this is the x value, and this is f of -4. If that's the case, then yes. If that's not the case, then it's not a point on the graph. So I will replace f of x or y by -6. And the right-hand side is -4 minus 2. -4 minus 2 in absolute value. I know that this is impossible because a negative number can never equal a positive number. That's never possible. This is -6 in absolute value, which is 6 units. 6 units can never equal -6 units. And I will say absolutely not. This point is not on the graph of this function because the point does not verify the equation. Any questions on how to verify whether a point is or is not on the graph? Okay. Graph this equation using the point plotting method. We are way beyond that. We know how to find the x and y intercepts because this is a linear equation and we graph them many times. So I'm going to skip this. If you have any difficulties with it, then we'll talk about it. But we are beyond this. Now this is a different story because this is a different function that we have not looked at before. So y or f of x equals -x squared plus 13. And they are giving us x equals -2, x equals -1, x equals 0, and x equals 1. This, I don't disagree with this exercise, but it's not really useful. at this point in time, but let's work on it. So we need to determine f of -2. We need to determine f of -1. We need to determine f of 0 and f of 1. Can anyone give us any of these numbers? And then I'll explain. Can anyone give us any of these numbers? F of -2.
The 15? No.
Anybody? -2 squared is 4, with minus in front is -4. 13 minus 4 is 9. F of -1,
Can you re-explain that?
when I square a negative number, I get positive 4, with minus in front is -4. 13 minus 4 is 9. F of -1, please. Anybody?
Is it 12?
Yes, it is. Good. F of 0.
13.
Good. And F of 1.
14.
1 squared is 1, with minus.
12.
Good. Very good. So now, this is not sufficient for us to understand the shape of this graph. So allow me to explain. This is a very important graph. This is a quadratic function. This is an absolute value function. Okay, so let's talk about the quadratic function. The simplest quadratic function is f of x equals 1x squared. This is the simplest one. It is very important early on to understand the graph and remember it. This is a very important graph. It will follow you everywhere you go in math, I promise you. And the graph is something like this. It holds water, so to speak. It's symmetric on left and right with respect to the y-axis. And it has a vertex or a turn at 0, 0. Turn, also called vertex. Now, the -1 in front creates a totally different situation. It flips the graph upside down. So if you want to look at the function g of x equals -x squared, it's identical graph, but flipped over the x-axis. So it looks like this. So this is g of x equals -x squared. This you should remember forever. The x squared, quadratic, the simplest possible quadratic equation. There is nothing simpler than this. This is the so-called basic quadratic function. And this one is a flip over the x-axis. Identical, flipped over the x-axis. This one has a minimum. This one has a maximum, both at the same point. Okay, this is the theory. But you can say, what are you doing with this? This is different. True. How do I graph something like that? I shift this graph up 13 units. So let's say this is 13, and this is my graph. This is y equals negative x squared plus 13. Now I would like us to see all these graphs with the graphing calculator. So we go to the graphing calculator. This is extremely useful. You're going to see this will come back later on. So x squared, that's for first function. The negative x squared, that's the second function. And then we want negative x squared plus 13. Before I hit on graph, let's look at zoom. Please select number 6, the standard viewing window. Okay, we need to understand what the standard viewing window in the calculator is. So this is the viewing window of the calculator. These are the keys and so on and so forth. And you will see the x-axis and the y-axis. So negative 10, 10, negative 10, 10 is the standard viewing window in the graphing calculator. Now, if I do hit standard, I will not see this point because it's at 13. So let's do that for a moment. And let's see what happens. And then I want to show you how to adjust the viewing window. So I'll click on 6. Please watch because this will happen very fast. So let's go back for a moment. Blue, I think it's blue, red, black. They will appear in this order and it will be very fast. So I'm going back to zoom. I'm selecting 6, which is the standard viewing window. And please watch what happens. 1, 2, 3. As expected, this is the basic x squared. This is the negative x squared. And see, the maximum here or the vertex was cut off. How do I adjust the viewing window? I know the y coordinate has to go beyond 13. So I'll go to window this time. And all I have to change is the y maximum. I want y maximum, let's say, to be 20. And then I hit enter again, or graph again, sorry. Quickly. 1, 2, 3. So the x squared, the negative x squared, and the negative x squared shifted up 13 units. So therefore, plugging in these numbers here is not going to help us graph. This is not enough. We need to understand how the graph looks like. We need to decompose it in small pieces. The first piece, the basic piece, which is x squared, then the negative x squared, and then the negative x squared plus 13. Plugging in these numbers here means nothing. And they want them as an ordered pair. So carefully, you have to put the ordered pair. And we found negative 2, 9. Negative 1, 12. Um, 0, 13. And 112. Okay. Use the 4-point graphing, la la la. It's not going to help. Okay, so -2, 9, and so on and so forth. It's not going to help because these points are not representative. What we have here, we have the graphing calculator, but the representative means the x and y intercepts. They are not there. We don't have those points. They did not even, so we do have the y-intercept, 0, 13, but we don't have the x-intercepts. Okay, so this is not going to help. So I don't like this exercise. Even if we plot all these and then we click save, the graphing calculator will not explain, the exercise will not explain to us why are we getting the shape we're getting. Okay, so where is -2, 9? So -2, 9 is somewhere here. Then -1, 12 is somewhere here. And then 0, 13 is somewhere here. And then 1, 12 is here. So I have these 3 points, but how do I know that this is the shape? I don't. Unless somebody is explaining to me how the system works and so on and so forth. Okay. Good, so please remember this graph. Now, graphing the absolute value of x minus 3 is a totally different story. And this is a very important function as well. So let's take a look. So for now, we know how to graph a quadratic. The basic one, the absolute basic one, this is a quadratic function, this. Y equals x squared. So we have to remember moving forward. This function will appear multiple times. Now the next one is the absolute value. But we have to start with the basic function, not whatever they throw at us. We have to start with the function f of x equals the basic possible, simplest possible function, the absolute value of x.